And here we go. Hello, Sean.
Hey, Joe. How's it going?
Thanks for being here again, man. I really appreciate it. So over the weekend, I got into your book. Woo.
Yes.
It's great. But
Thank you.
I mean, I really appreciate someone like you who's trying to break down quantum mechanics and quantum physics for someone like me. It's very hard to follow. And there was a lot of backing up and trying it again and backing up and trying it again and like going over paragraphs and trying to figure out exactly what it means. But it's really excellent and really perplexing at the same time.
Well, thank you. And, there are different styles when it comes to writing popular books. And I think there should be different styles. And my particular style is, look, it's not going to be a breezy page turner.
Right.
But if you read it carefully, like there's not prerequisites. You don't have to come into it as an expert. What you have to come into it is someone who's willing to sit and think about every paragraph. And then hopefully it will be rewarding and you'll truly understand what's going on after doing that.
Well, it is rewarding because it is fascinating. And the history of quantum physics is also pretty fascinating because I've always wondered, like, how did anybody even want to come up with this stuff? Like these... Yeah. And the fact that it was so long ago was what the beginnings of it were in the 19th century?
1900 is the typical, literally that year, the turn of the century when Max Planck first got the first hints of it. And then, took another 27 years to put it into final shape.
Now, for regular people that don't have a background in physics or that don't, this is like the whole idea behind it is so bizarre. It's like, why would anybody try to figure out something that one of the things that you said that's really interesting is that quantum physics is used all the time. Right. It's used with exact calculations, but yet we don't really understand it.
Yeah. That's the main message of the book, really, because physicists, of course, do quantum mechanics every day, whether it's, straightforward quantum mechanics, quantum field theory, quantum information, quantum computing. Clearly, we're pretty good at it, like transistors and lasers depend on quantum mechanics. The sun shining, figuring that out depends on quantum mechanics, the Higgs boson, etc. So to claim that we don't understand quantum mechanics is a little bit weird, but then we have quotes from people like Richard Feynman saying nobody understands quantum mechanics, right? And so if he says that, then there's some authority behind it. And the reason is what we have is sort of a black box, right? We say, what I said in a New York Times article I wrote recently is physicists understand quantum mechanics in the same way that someone who owns a smartphone understands the smartphone. Like they know how to use the apps. They can call people. They can make phone calls. They can take pictures. They don't know what's going on inside. And that's physicists with quantum mechanics. They use it. They can make very, very precise predictions. But if you ask them what is really going on, like what is actually happening, what are all the details, they're like, no, that's not our job. Let's just stick to predictions.
But to someone like me, that's so terrifying because like the very nature of reality is being examined by people. Like if it is a smartphone, it's being examined by people like me.
Yeah.
Who don't really understand the smartphone. I have no idea what's going on inside a smartphone. I know some words that have used to describe RAM and processors. There's
probably electrons moving around in there, right? But and I think, and in some sense, that's fine. Like most of us don't need to know what's going on inside the smartphone to use it, but somebody should know, right?
Yes.
And my argument in the book is, look, if 500 years from now, when historians write the history of 20th century physics, they will say two things. One is, my God, these people were so brilliant and creative to invent quantum mechanics. And then they were so afraid to really take it seriously and try to understand it. Like they said, stop asking questions about the meaning of reality and what the world is doing. In my mind, what physics is all about is understanding reality and what the world is doing. It's not just about making predictions. Making predictions is good, but we do that, mostly because we're curious about what the world is doing.
Well, for people outside the world of academia, when I read someone like you saying that you were discouraged from pursuing this, and you were literally told that you should be pursuing your work in cosmology and gravitation, that's where it's at.
That's serious work, yeah.
Yeah, that seems to me be so crazy. It's like if anybody should be pursuing it, it should be people like you.
I mean, I want to be fair. So, of course, 20th century physics was incredibly successful. And there was part of the attitude was, look, we have to understand nuclear physics and particle physics. And, a lot of it was the center of physics shifted from Europe to the U.S. And Europe is much more philosophical and willing to think about the deep ideas. And Americans are pretty pragmatic and want to build things, right? In particular, at the time, they wanted to build nuclear weapons. And so the idea of just really putting aside deep philosophical issues and putting stuff to work was attractive. And the other issue is, okay, let's say we do demand that we understand quantum mechanics better. How do you do it? Like, what experiment is it there that you can do? As
Right.
far as we know, the cookbook that we have, even though we don't understand it, works pretty well. Like, what could you type into your smartphone that would help you understand what's going on inside? It's kind of hard to figure out. So I think that those attitudes were wrong, but at least, they're not completely crazy. It's not just that they were afraid of the truth or anything like that. And I also think that it is finally changing now. I think that there's slowly, more people are appreciating that understanding quantum mechanics is important.
What do you attribute that to?
A couple of things. One is, there's good news and bad news. Part of the good news is technology has gotten better. So we're trying to build quantum computers, for example. And guess what? Some of the ad hoc rules that we had for doing quantum mechanics might not be up to the task. We need to understand the details a little bit better. The other sadder thing is that so much of fundamental physics is kind of stuck right now, right? We literally have not been surprised by a new experimental result in fundamental physics since the 1970s.
Whoa.
There's one exception to that, which is the universe accelerating in 1998, which was the dark energy. We've had amazing accomplishments in experimental and observational physics. We found the Higgs boson, we found the top quark, we found gravitational waves, the microwave background, many, many things. But they were all predicted decades ago, right? So progress is driven by being surprised, and it's been a long time since we've been surprised. So some people, including myself, say, well, one of the things to do in that situation is to take a step back and re-examine the foundations. Maybe we can take a broader look and think that we're walking down the wrong path.
Now, for people that don't have any background in physics, there's a bit of an issue with public perception. And one of the things about public perception is films like What the Bleep.
Yeah.
That sort of throw this sort of cultish monkey wrench into the, quantum physics is weird enough as it is.
Yeah.
Without adding that movie was literally created by a channeler, right?
A friend of mine, David Albert, who is one of the leading philosophers of physics, and I should also give credit to philosophers here because they have been taking quantum mechanics seriously longer than the physicists have, to be honest. So David is one of many people who got a PhD in physics and then switched to philosophy because he cared about the foundations of quantum mechanics, and no physics department would ever hire him, right?
That's hilarious.
And I tell the
He had
story.
to go in through the back door.
Yeah, I tell the story in the book. Like, he wrote a bunch of influential papers as a graduate student, and then he went and said, I would like to, make these papers my PhD thesis. And they said, no, that's not really serious physics. And they punished him by making him write this incredibly technical mathematical paper on quantum field theory just to prove he could do it. And then he's like, I don't want to take this anymore. I'm switching fields. But anyway, he was in that film. He was in What the Bleep. And they lied to him. They misrepresented themselves. They said, we're doing a documentary about quantum mechanics. And they sat him down for 3 hours and asked him all these questions, leading questions like, doesn't this mean that we're bringing reality into existence by looking at it? And he's like, no, that's not what it means. Let me explain to you. And then in the final film, there's like 30-second clips of him going, yes, that is a really important question, right? Like completely misrepresenting what he said. And so he went public after that and complained about the film. And he did, in a hilarious story, there was a event, some sort of convention put on in Santa Monica by supporters of the film that they thought it would be fun to get all of the people who were in the movie, What the Bleep Do We Know, and get them and talk to them and charge people money to listen to them. But these people were not affiliated with the filmmakers. So they didn't know that David Albert had been completely misrepresented in the film, so they invited him. And he goes to this event in Santa Monica, and he gave a talk. He decided, he wondered, like, should I just go at all? But okay, why not? Let's reach a different audience. And he gave a talk, and he said, look, there's two things you can do. when you are faced with fundamental puzzles of reality. One is you can face up to what the world is trying to tell you, and you can accept it and take it as what it is, no matter what you like. The other is you can choose to tell a flattering story about yourself. And the people who made this movie have decided that the mysteries of quantum mechanics are really stories about how they are powerful and have influence over reality and so forth, but it's all nonsense. And the punchline is the audience loved it. They went nuts because what they wanted was a guru of some sort, and like he was just as good a guru as anybody else. Right. So he had a better story to tell.
A reality-based
guru. Yeah. So I think you're right. I mean, I think that quantum mechanics, I've said before, is of all the theories in the history of science, the most easily distorted and misrepresented in the popular mind.
Well, you've done an amazing job in this book of trying to boil it down for dummies like me, but it's hard. It is a complicated and insanely nuanced subject.
Yeah.
And it's one of those things where it like this many worlds theory, for one example, the just the possibility that there's like explain that.
Sure.
Explain for people that don't understand what quantum mechanics even means. Give them just like a little bit of that, and then explain many worlds theory.
Yeah, good. This is what I'm here to do. So,
thank you.
An electron. Take an electron. Quantum mechanics should apply to the entire universe, but it becomes unmistakable when you look at little tiny things, right? So we always are talking about electrons or atoms and so forth. An electron has a position, and well, sorry, let me not even say that. Even that was wrong. It's just so hard to correctly talk about quantum mechanics, right? If you were Isaac Newton, before there was quantum mechanics, there was classical mechanics. And basically, quantum mechanics and classical mechanics are the only two big frameworks that have ever existed in physics. Classical mechanics was so good that everyone thought that was just right, and it was all a matter of filling the details until quantum mechanics came along and changed things. In classical mechanics, an electron is a point. It has a position, a location in space, and it has a velocity. It's moving somewhere. And from that, you can predict what's going to happen. Okay? Quantum mechanics says, no. The electron has a wave function. So there's a wave. Sometimes you hear this debate about are things like electrons and photons particles or waves. The answer is that they are waves. And the wave function has this weird property that when you're not looking at it, it's a wave, it's all spread out or it's localized somewhere, but it obeys an equation, the Schrodinger equation. So far, so good, just like regular physics. There's a thing, the wave function, it obeys an equation, the Schrodinger equation. You can predict what's going to happen next. But the weird thing about quantum mechanics is that there's a whole separate set of rules for what happens when you look at the thing, when you observe it, when you measure it.
That's where things get squirrely with people describing it, right?
Yes.
And that's where they want to go woo-woo on you.
It's an opening to be woo-woo, right? When you say, like, what do you mean observe something? Like, does it have to be a conscious being? Can it be a video camera? That's just weird, right?
Is it the act of measuring that changes things?
Well, this is the puzzle, okay? This is what is called the measurement problem of quantum mechanics, that the rules we teach our students at Caltech or anywhere else when we teach them quantum mechanics in their sophomore year of college, the rules say when a system is observed, when it is measured, its state, its wave function, changes dramatically, suddenly, and unpredictably.
Now, let me ask you this. How do we know this based on if you're measuring it and it changes? How do we know? Because we didn't measure it before. Like, what observations are we making that we understand the state of it before it's measured without measuring it?
Good. There's a couple of ways. So let me make things even simpler. Forget about where the electron is located and think about the electron is spinning. Right? Okay. The electron is spinning just like the Earth spins. It's really exactly like that. It's like a little spinning top, except when you measure the spin, you can sort of send the electron through a magnetic field and it will get deflected either up or down, depending on whether it's spin up or spin down. You only ever get one of two answers. It's either going up or going down. It's nowhere in between. This is an empirical measured fact, okay? So that's a part of quantum mechanics. That's the quantum fact, that there's discrete set of possible answers to this question. Is it spinning clockwise or counterclockwise? Yes or no. It's just those two possibilities, nowhere in between. So if you have a magnetic field that is oriented vertically, send your electron through it, it gets deflected up, you say, oh, it's spin up. So now I've measured its spin. Now I know what its state is. If I send it through another magnetic field or oriented vertically, it will always be deflected up every single time. We know what it is. We're going to measure it. Measuring it in this case doesn't change it. It's in exactly that state. We know it, okay? Now let's send it through a magnetic field that is oriented horizontally. So it's going to be deflected either right or left. We know exactly what state it's in. It's spinning this way. But when you send it through that magnetic field that's oriented horizontally, it gets deflected left or right 50-50, unpredictably. There's no way we can predict it. And then once it is, so okay, now it's been spinning up. You measured its spin left, let's say. Send it through another magnet that is going vertically. And now it's 50-50 again. It could be spin up or spin down. So somehow, even though we knew exactly what state it was in, we couldn't predict what would happen next. That is part of quantum mechanics.
So the act of sending it through these things where it makes it vertical or horizontal, what is happening to it when it's going through these things?
So in quantum mechanics, what we say is that it's not that we don't know whether the electron is spinning clockwise or counterclockwise. It can be in a superposition of both. That's just the spin version of the position of the electron can be spread out in a wave, right? It's truly not just that we are lacking some knowledge. It's that the knowledge really isn't there. And again, this is how we teach quantum mechanics in textbooks. And then I'm going to correct it because Many Worlds is much better. But This is the standard textbook version. There's a wave function. The wave function for a spin is it's either up or down or some combination. And then there's a rule that says when you measure the spin, you only get up or down. You don't see the wave function. Just like the cloud that you have for the electron's position, when you look at it, you see it at a location. So another way to make the same argument is take a little piece of, I have a nice little image of this when I give talks, a little piece of uranium. So it's a radioactive little chunk of metal, and you put it in a bubble chamber. So it is emitting radioactive particles, and you detect the particles. You can see a little streak of motion when the particle leaves the uranium, okay? Well, like I said, when you're not looking at it, this electron is supposed to obey an equation, the Schrodinger equation. And you can ask what the prediction is when a radioactive nucleus decays and gives off an electron. What is its wave function going to do? What is the wave function of the electron going to be? And the answer is it goes off in a spherical wave. It goes off in all directions at once.
Evenly.
Yeah. All directions evenly. But you never see that.
Is that roughly based on the shape of the piece of uranium? Does it vary?
No, because the electron gets from one individual nucleus of an atom, right? So what the uranium is doing doesn't matter. It's just that one atom matters. And the easiest thing for the electron to do is just to go out in a sphere. It doesn't have to. It can go out in higher energy states. But the point is, it's not going out in a straight line. But when you look at it, you see a straight line, right? That's the fundamental mystery of quantum mechanics, that how we describe the thing when we're not looking at it is different than what we see when we look at it. So
when you're in pursuit of an understanding, a deeper understanding of quantum mechanics, when you're thinking about people from the 1900s that are just sort of basically getting the first steps going to understand this stuff, when you're talking about this lack of funding and the lack of encouragement for people to pursue quantum mechanics, you strongly feel like there are answers to these questions.
Yeah, that's right.
That we just need better tools and a better understanding, better equations, more time.
Yeah, me and Einstein think this, right? So Einstein is one of the secret heroes of the book because he has this reputation as someone who just couldn't quite accept quantum mechanics. The title, Something Deeply Hidden, is a quote from Einstein when he was talking about when he was a kid and he had a compass, right? And he was given his first magnetic compass and he could rotate it this way and that way and it always pointed north. And you and I would go, that's cool. But he was Einstein. He's like, wow, this is amazing. Why? How does it know where north is, right? And he said there must be something deeply hidden that explains why it's doing this mysterious thing. And he felt the same way about quantum mechanics, that we gave these set of rules, which are called the Copenhagen interpretation of quantum mechanics. One set of rules for when you're looking at it, one set of rules for when you're not. And Einstein was like, oh, come on. Clearly, this is not the final answer to the nature of reality, right? He wanted to know God's thoughts. He's like, I want to know everything. We're not done yet. There must be more going on. And so Many Worlds is one of the proposed answers to what could be going on. It's not the only one. There's alternatives, but it's definitely my favorite. It's definitely the easiest one to write down. Let's put it that way.
Okay, so hit us with this many worlds theory.
Okay, so think about this electron. You say that it could be either spin up or spin down. It's a combination of both. That's its wave function. You measure it, you only ever see spin up or spin down. So Copenhagen says that's because the wave function suddenly changed, snapped into place when you observed it. Don't ask me what it means to observe something. That's not what Copenhagen lets you ask.
Okay.
Many worlds says what you're missing is two things. Number one, you're a quantum system. You're obeying the rules of quantum mechanics. You're made of atoms and electrons and so forth. You have a wave function too, okay? So you're secretly treating yourself as a classical thing when you make that measurement, but you really should be treating yourself quantum mechanically, right? That's one thing. And the other thing is something that Einstein invented, namely called entanglement. When quantum mechanics says there's a wave function for a system, it doesn't say there's a separate wave function for every particle. Right? It says that there's only one wave function for the whole universe. So the way I like to say it is, imagine two particles come in and bounce off of each other. Either one has a wave function and it's unpredictable exactly what angle it's going to go off at. So both of the particles that go off, you don't know where they're going. But because momentum is conserved, if they came in at equal velocities, they'll go out at equal velocities and in opposite directions. If you measure one, then you know where the other one is going, right? That's entanglement. The observed state of one system can be related to the observed state of another system. So those are the two ingredients. You're a quantum system, and quantum systems can be entangled with each other. So Hugh Everett, who was a graduate student when he invented this idea in the 1950s, said, look, when you measure that electron, what happens physically? Like, forget about you're a person, you're conscious, all of that BS. Like, you're a physical system, you obey the Schrodinger equation. You are a quantum mechanical system, you obey the laws of physics. So you look at the electron, your wave function changes. It used to be you're just a person doing whatever you do, but then after you look at the electron, you become entangled with it. And it splits. So there is one part of the wave function that says the electron was spinning clockwise and you measured it spinning clockwise. And there's another part of the wave function that says the electron was spinning counterclockwise and you saw it spinning counterclockwise. Now, everybody knows this. Like that far, it's not controversial at all. That's clearly the prediction of the equations of quantum mechanics. But everyone else said, well, that means that I'm some weird combination of I saw it spinning one way and I saw it spinning the other way, but I've never felt that way. When I look at real electrons, I see them one way or the other. That can't be right. That can't be the final answer. The wave function must somehow collapse. And Everett said, no, what you're missing is there's now two separate worlds. Both of those part of the wave function are real, but they're different worlds. They will never interact with each other again. What happens in one part of the wave function will not affect what happens in the other part. So now there's a version of you that saw the electron spinning clockwise, and there's another version of you that saw it spinning counterclockwise. And that's just taking seriously the prediction of quantum mechanics. It's not adding any extra stuff, any extra worlds, anything like that.
That is the part where my brain broke.
All right.
The idea that there's a you that observes it going clockwise and a you that observes it going in a different direction, like that is so hard to understand. Do you apply this in your regular life? Like, do you think, like when you go home and you say hi to your wife and you open up the refrigerator, do you think of yourself as this quantum being that's existing in this super state?
So, I mean, there's a couple of answers to that. One is, sure, if I think about it, like I really do believe it. I have a chapter in the book, which my editor resisted at first, but then he let me get away with it, which is a dialogue between a young philosopher and her father, who is a physicist. And the father is skeptical about all this philosophical nonsense, and she tries to explain how many worlds works to him. And at the end, his last question is, do you really believe this? Are you really taking this seriously? And look, that's a perfectly good question. It's a very respectable question because it is many worlds. It's not crazy or weird or bizarre, but it's certainly very, very far away from our everyday experience, right? So what it's asking you to do is to say, I have these equations. They are really, really good at fitting what I do observe in the world and making predictions. I can build the Large Hadron Collider, et cetera. I will take them seriously even for things that I can't directly observe. Because they're the best equations I have, right? Until a better set of equations come along, I will believe these equations. And the implication of that is, yeah, there's a whole bunch of worlds, like a huge number, like a real, humongously, unimaginably big number, maybe an infinite number, maybe finite, we don't know, of different copies of you, and they're being created all the time. The good news is that it doesn't really affect how you go through your life. It doesn't really imply that you should behave any differently than you would if you just lived in one world.
But do you think of each choice that you make possibly changing everything about the world that you exist in? How are you looking at it? You know what I'm saying? Because you are a guy who probably understands it as good as anybody that's alive. So as weird as this stuff sounds, to me it sounds like it's almost impossible for me to comprehend. So I'm trying to filter it through your understanding of it.
Well, I think that...
He's taking his jacket off. We're getting serious.
I know. It's getting hot in here. Physics is heating us up. I'm not exactly sure how to say it the best. It doesn't change who you are. It's certainly not true that you making a decision is what branches the wave function of the universe. I guess that's the right thing to say.
Good, because I want to stop all woo.
Yeah, you can't do that.
Before it happens.
Everyone, believe me.
Hit the brakes.
The joke about how certain political choices imply that we're living in the wrong branch of the wave function has been made many, many times, right? But
okay.
It's not that your choices create different universes. Different universes get created, and maybe you're different in them by a little bit. In fact, I like to point out there is an app you can download if you have an iPhone called Universe Splitter, which will branch the wave function of the universe for you. And then if you agree ahead of time to do one thing in one branch and another thing in another branch, then there will be multiple copies of you who are living different lives. And then you can deal with that and your therapist however you like.
But what is the application exactly doing?
What it's doing is basically a version of measuring the spin of
It's called Universe Splitter?
Universe Splitter. It's only for iPhones.
I'm going to grab this right now.
But,
sorry, Android people.
Yeah, sorry. It's not even a web page. It's only an app. There's equivalent web pages. But.
Okay, I'm pulling it up right now.
Yeah, and what you can do, basically it sends a signal to a lab that coincidentally is located in Geneva, Switzerland, but has nothing to do with the Higgs boson or anything like that. They send a single photon down a pipe to what's called a beam splitter. So the wave function of the photon goes 50-50. It gets sent left. It gets sent right. And if you agree, and so then it sends back whether you ended up in the branch of the wave function where it went left or where it went. There you go. 199. Come on.
Yeah.
The power of changing the universe is in your hands.
I downloaded it.
Good.
I got it. I paid for it. I got it right here.
Yeah.
All right.
So if you have any tough choices, you can type in, I want to have pizza or I want to have Chinese food for dinner tonight.
Well, it says in one universe, I will take a chance. In the other one, I will play it safe.
Yeah, but you can correct those. You can fill in whatever you want.
Really?
Yeah, that's the good part.
But what is happening with this
I will
app?
ask her to marry me. I will not ask her to marry me.
Is this
I will accept this job. I will go somewhere else.
Equivalent of a quantum fortune cookie?
Yeah. But
yes.
Except that all possible fortunes are obtained in different universes. The bad news is you can't ever find out how things went in the other universe. You can't talk to the different universes.
That's the problem, right?
Yeah, that's
so
the problem,
people will be paralyzed by analysis.
That's why you should act the same as if you just lived in one universe, because you can never talk to the people in the other ones.
So, but now let's hit the brakes on the woo again.
Yeah.
Because people would like to believe that there are there an infinite number of yous existing at the exact same time, making various choices which send you off in different directions?
So, number one, we don't know if it's infinite number or just really big, but there's certainly a really, really big number. It's big enough to be, big enough for whatever you want. But it's not everything. The theory does not say everything happens somewhere, right? The theory says the Schrodinger equation is obeyed. There's an equation that is obeyed. So electrons will never convert into protons because electrons are negatively charged and protons are positively charged. And nowhere in the Schrodinger equation can you violate the conservation of charge, right? So there's plenty of things that don't happen, but then there are plenty of things that do happen. And some things are more likely than others for you to experience. So again, it's sort of it's a mind-bendy thing, but it's a straightforward prediction of the equations, and it doesn't affect our lives. There's no rule that says, to be a moral person, to be a good utilitarian and make the world happy, knowing that the wave function is branching into multiple copies, I should act differently somehow. It's exactly the same as it would be in the ordinary world.
So, you are the ordinary world, no matter how many copies of you there are, or how many versions of you there are.
There's nothing. So when all these copies are being made, there's no essence of you that is traveling through one of the copies, right? Like all of these people are separate people. So I use the analogy, it's like identical twins. They were the same zygote or whatever, and now they're different people, okay? So that's the same thing. Like you're you now, and if you hit the button and branch the wave function, there'll be two different people, both of whom used to be you, but they're not the same person anymore because different things happen to them.
Now, when people think about the concept of quantum mechanics and the way you're talking about it, describing things in the micro and the macro, you think of your existence itself in a very similar manner, the way you think of electrons, the way you think of things being quantum, is that you are a combination of all these quantum things.
Yeah.
So you don't operate in some sort of static state that's very like here and now and carbon, and you can put it on a scale and it'll never change. There's constant versions of you.
Yeah, it's kind of like a whooshing where more and more versions of you are being created all the time, and it's an interesting thing because even the best trained physicists sort of think intuitively classically. Like, look, here's a table, there's a bottle, right?
You have to.
You have
Red
to.
light comes, hit the brakes.
And this is how we evolved, right?
Yes.
This is how our brains work, right? And like I said, many worlds is one respectable version of quantum mechanics. There are other respectable versions, more respectable than the textbook presentation. But they all the other ones somehow lean on our classical experience. And the textbook version certainly does. It says, like, you're a classical person observing a quantum mechanical system and so forth. And Everett, when he was a graduate student, he had arguments across the ocean with people in Copenhagen, who tried to push their way forward. And he's like, why do you get to be classical and the electron has to be quantum? Like, why aren't you quantum? Like, why isn't everything, what's so special about you, really?
Right.
And he was trying to think of the quantum mechanics of the whole universe, right? Where he's not a separate observer outside because he's doing the whole universe all at once. And so everything had to be quantum. And I think that's another thing that is pushing us to appreciate the foundations of quantum mechanics a little bit more, is that we're trying to understand quantum gravity. We're trying to understand quantum cosmology, the universe all at once, obeying the rules of quantum mechanics. And the conventional Copenhagen theory is just not up to it.
When I was reading it, I was thinking, a thought came across my mind that it's almost like the human brain is a radio that's picking up a distant signal but getting better and better at tuning into it all the time. And that we are thinking of ourselves in this very limited, primitive, biological way because that's how we evolved. But slowly but surely, through people like you and through work on this stuff, we're gaining this more comprehensive view of what reality is itself, and that we're experiencing these stages of comprehension. And that's why, again, going off of what you're saying about you're being potentially discouraged from pursuing these things, that's why this is so important. Is like, for most people like myself who don't have a background in this at all, the signal is so distant. But it seems like the more you folks study it, and the more the Large Hadron Collider and CERN and more these experiments get done, the closer we get to just a better signal, just a little bit better signal. And we might be talking about generations from now.
Right, exactly. Yeah, but no, I like the analogy very much because the human brain did not evolve to understand quantum mechanics, right? It didn't evolve to understand science at all. Like some of my best friends are human beings, but we are wonderful bundles of impulses and heuristics and shortcuts and ways to rationalize our behavior and stuff like that. And the idea that we can aspire to be logical and to develop theories and reject them and to develop theories that are very, very far away from our everyday experience is a relative latecomer on the evolutionary scene, and we're still not really good at it. We're getting better at it. And this is part of it. Quantum mechanics is the biggest challenge that we have in physics to our intuitive understanding of the world. And so there's a question, how should we try to understand it? How much of it should we lean on our intuitive understanding, and how much should we just accept that the world is fundamentally super duper different? And I think that's a perfectly good question. I'm not trying to prejudice the answer one way or the other. I mean, our experience is limited, but it's all we have, right? You know, we have to be based on that. And so some people wonder, is quantum mechanics just impossible to understand? Like, is the human brain not up to the task?
The current human brain.
The current human brain, sure. But I think that that's totally wrong. I think that, number one, quantum mechanics certainly is very understandable. And number two, I don't think that anything about nature is impossible to understand for the current human brain. I mean, maybe it is. There's no way of knowing for sure. But there's zero evidence that we will fail in our ambition to try to understand the universe. It's just hard and it takes time. Look, 100 years ago, we didn't have quantum mechanics at all. Like, we've made enormous progress, and 100 years is nothing, even in human history, much less cosmological history. So don't be impatient. Take time.
But it just seems to me that the human understanding of the world we live in is obviously radically changed over the last 500 years. And if we continue to exist in this current state or a slightly better state as things move on, it's going to get better. But quantum mechanics and quantum theory to me almost seems like an ant trying to understand the choices on Netflix. It's like those choices exist, but the ant really lacks all tools. I mean, without people like you, especially describing the computations and what's been done and what we currently understand. For a regular person with no background or even no knowledge of it, no one's ever explained it to them at all.
Yeah.
It's almost outside of the realm of our capacity for reasoning.
Nope, I got to disagree.
Okay.
I think it's just hard. I think there's a difference. I think that, and I could be wrong about this, but I think that, there was a phase transition. There was some, how we talk in computer science about a certain kind of computational machine being Turing complete. I mean, maybe you don't know this, but this is something we say.
Please explain that.
So a Turing machine, Alan Turing, the great computer scientist who broke codes and things like that, he also thought a lot about like what computation was, and he invented the Turing test for consciousness and stuff like that.
For AI, right?
And for AI, yeah. But the Turing complete is basically there's a certain kind of computational device that can essentially do any computation that can be done. Like anything, you can ask if you can do this problem, then you can also do that problem, and there's sort of a maximal hardness to problems, and so a Turing machine can do that problem if you give it enough time. And there's some problems that are undoable, so no machine can do those, but the doable ones can be done on a Turing complete machine. So in some sense, this is not a rigorous fact by any stretch, but I think there's an analogy with human reasoning. Like at some point, we're a little bit smarter than dogs and cats. But it's not just we're a little bit smarter, we're a different kind of smart. Like we did pass a threshold. We can use language. We can reason symbolically and abstractly. We can write things down and pass them down through generations. We can imagine futures in ways that they can't. So even though, the number of neurons or the number of connections in our brain might not be that different between a human being and a chimpanzee, it's a different kind of reasoning that has been opened up. We've become capable of this kind of thought. And I think that's enough. My idea is that we are smart enough to understand the laws of physics, whatever they turn out to be, quantum mechanics or something beyond quantum mechanics. And to the person on the street who's never learned anything about quantum mechanics, it is so different from how you experience the world that it seems bizarre, and you do have to read the same paragraph over and over again sometimes, but I think it is absolutely understandable if people make the effort. I don't think there's any person who, can balance their checkbook but not understand quantum mechanics.
They just need to put the time in.
Yeah.
Put the time in and take your time and go
and
back.
And be open.
Yes.
Don't the real thing that holds people back, I think, is insisting ahead of time that they know how things work, right? That reality should work in a certain way.
Yes.
And you have to at least be open to the possibility that the way reality works is way different than what you had in mind. If you're open and you're willing to put in the work, you can understand it.
That's why I was curious as to how you apply it in your actual physical life. Your knock on wood, ring a doorbell, drive a car, physical life.
Yeah, if I was thinking about quantum mechanics when I was driving my car, things would be much worse than they are. And that's because the classical world is a really good approximation. I mean, this is something I'm also interested in. Yeah, this is important. Emergence, right? I talked about this in the last book, in The Big Picture. think about this. When we talk about the Earth going around the sun, forget about quantum mechanics. Just do classical mechanics, Isaac Newton, Earth orbiting the sun, okay? We can predict that. We can write down the equations. We can tell you where the Earth was 1 million years ago or 1 million years in the future, right? But think about how amazing that is. The Earth is made of something like 10 to the 50th atoms, okay? In principle, to tell you what the Earth is doing, I should tell you what every one of those atoms is doing, right?
Yes.
But I have no idea what every one of those atoms is doing. All I actually in the real world need to tell you to predict what the Earth is doing is to tell you the center of mass of the Earth, where it is and where it's moving. So only using an incredibly tiny amount of information, I can make incredibly precise and accurate predictions. I have this enormous handle over what the world's doing, ignoring almost all of the data that there is about the specific state of the world. So that's emergence, when you don't need to know almost anything about a system. You have certain very, very special high leverage pieces of information that you can use to make accurate predictions. So really, now that we know quantum mechanics, all of classical physics is like that. The fact that you can throw a baseball and know where it's going to land and stuff like that, the fact that you can get a rocket to the moon or drive a car is because, without knowing quantum mechanics, is because Newton's laws of physics are a really, really good approximation that let you make predictions without knowing the quantum wave function of the car you're driving, right? And if you needed to know the quantum wave function of the car you were driving, it would be hopeless. It's just, computationally intractable. So the world appears to us in a way that that is very convenient in some ways. We need to know so little about the world to yet understand quite a bit of it. Otherwise, we couldn't get through the day.
The idea that everything is in motion is also very difficult for people to wrap their brain around. You see a stationary rock on the ground.
Yeah.
You think that rock is still, but it is not. Nothing is still.
It's pretty still.
But it's a part of the Earth.
It's pretty
and the Earth
still.
is spinning.
Sure, the Earth is spinning.
So relatively,
that's right.
In terms of the universe, everything is in motion in some way, shape, or form.
Well, there's a lot going on here actually, because on the one hand, Einstein teaches us, when you say something is moving, you have to say with respect to what?
Right.
Right? So if you're standing next to the rock, it's not moving with respect to you, right?
Mm-hmm.
If you're just stationary there. There's also what I try to squelch in the book. One of the misunderstandings about quantum mechanics is the idea of quantum fluctuations. The idea that an electron sitting in the orbit of an atom is really jiggling around there and you don't know exactly where it is. That's not what quantum mechanics says. Like if you're a good Everettian anyway, a good many worlds person, there's a wave function to the electron and the wave function is sitting there not moving. It's really not changing appreciably over time. If you were to observe the electron, you would see it somewhere, and if you were to observe it multiple times, it would be in different places, so it looks to you like it's jiggling around. But when you're not looking at it, it's not jiggling. It's just sitting there quietly, according to quantum mechanics.
So is this confusing description based on our limited ability to perceive?
It's actually based on the fact that we inevitably attach a notion of reality to what we do perceive, right? Okay. So in quantum mechanics, what we perceive is different than what really is. And that really bugs people because I just saw it. I mean, how much more real could it be, right? The way that we describe, I go on a rant in a whole chapter of the book, like the Heisenberg uncertainty principle, that there's uncertainty to either your position or your velocity. You can't know both of them at the same time. It's not that you can't know both of them at the same time. It's that neither one of them exists. Position and velocity are things you measure. They're not the elements of reality that quantum mechanics uses. And there's a difference there, and people don't like that. But by the way, I wanted to bring up yet a whole other aspect of the not moving thing, which I think is fascinating. And it's nothing to do with quantum mechanics, but it is a future frontier for physics, I think. We can look at the bottle of water and say, like, it looks pretty stationary. It's not really changing. I can also look at you, and you're sitting there pretty quietly. You're not really changing. But there's a tremendous difference because this is stationary, not moving, because all of its pieces are stationary and not moving. I mean, this is liquid, so it's not the best example. The table would be a better example. But you and I are sort of macroscopically stationary, trying to sit here more or less quietly. But inside, there's a lot of churn going on, right? There's, a lot of cellular biology. There's ATP is being created and destroyed, and, signals are going from our brain and back and forth. And someone like Antonio Damasio, the neuroscientist, emphasizes this idea of homeostasis, that there is stuff going on beneath the surface, but it regulates our particular configuration so that we are more or less macroscopically stable. And amazingly, human beings last for a century. Like, we're born and our bodily integrity lasts for 100 years, which is kind of crazy. But it doesn't do that by having its individual parts remain quiet and stationary. It does that through the arrow of time and the growth of entropy and the fact that we eat food and get sunlight and we use up enormous resources for the purpose of apparently maintaining our integrity. And I think that how that whole story works and fits together is something that physics doesn't understand very well, but will be important going forward.
The idea that there's an enormous number of you making various choices.
Yeah.
And that these various choices will ultimately affect how long you exist.
In some branches. So there is a weird thing called quantum immortality, which I think is a bad idea, and I don't like to talk about it, but people hear about it, so I sometimes need to mention it. Max Tegmark, who is a friend of mine and a very smart guy, popularized this idea. He said, look, and it's a little bit macabre, sorry about this, a little bit weird, the experiment, but imagine you're playing quantum Russian roulette. So you have your universe splitter, okay? You have your app on your iPhone, and you split the universe, and if it goes one way, you don't do anything. If it goes the other way, faster than you can react, a machine is activated that kills you instantly. Okay, so you don't even know it. You don't even perceive it. You don't have any pain. You're just instantly dead. And you do this over and over and over and over and over again. So in most branches of the wave function, you're dead. But in those, you're dead. You don't know anything. You don't feel like you're dead. There's no regret after the fact. The only version of you that survives is the one that was lucky enough to be in the branch where you didn't die every single time. So Tegmark's argument was that if you do this over and over again and you survive, you should take that as good evidence that the many worlds interpretation of quantum mechanics is correct. Because in other versions, you probably just died, right? I don't think that's quite right. I don't think that's a good way to go through your life. I think that the reason why we don't want to die is not just that we will experience pain, but that sort of prospectively, right now, the idea of being dead in the future bothers me, right? Mm-hmm. Like if someone said, you're going to die in this and that date, it might be useful information, but I'd be sad, right, if that date was soon. And I think the same thing is true in the quantum immortality experiment. I don't buy the move that says, well, in all the branches where you're dead, it doesn't matter because you're dead. You don't feel anything. Like, I think that right now it's okay for me to be bothered by the prospect that in many future worlds I will not be there. So, I think that at the end of the day, once again, you should act in quantum mechanics just like you act in the regular world. Are
there competing theories to this many worlds theory that you've embraced and then discarded?
Yeah. There's two big ones that are quite popular. One is more or less what Einstein had in mind, which are called hidden variable theories. So basically, if you have an electron and you say, look, when I'm not looking at it, it's wave-like. When I look at it, it's like particle-like. Maybe it's both. Maybe there is a wave and there is a particle. So in a hidden variable theory, there's a wave function, just like there is in many worlds. But there's also another set of variables saying there's really a location of the electron, right? Maybe I don't know where it is, but there really is an electron located somewhere. And that location of the electron is pushed around by the wave function, but it's a whole new part of reality. So there's separate branching of the wave function and all that stuff, but none of that is reality. Where reality is where the particles are. And this is now called Bohmian mechanics. David Bohm in the 1950s developed the most respectable version of this. It's sort of therapeutic if you don't like all the other worlds. It's basically, the equations are the same as many worlds, except there's new equations and new stuff. So it complicates the theory by adding new variables. But the good news is it says only one of the branches of the wave function is real. I don't need to worry about the other ones. The problem is it's very hard. My particular problem is it's very hard to reconcile these ideas with modern physics. Like if you thought the world was made of individual particles, it would do okay. But these days we use quantum field theory and quantum gravity and things like that. And those more modern ideas are harder to attach hidden variables to. So hidden variables are, an old idea, but I think that they're hard to make work. The other idea, which is more dramatic, a little bit more fun, is Every single electron has a wave function, and it seems to you that when you observe it, it collapses. But maybe what's really going on is the following, that there's a random probability every second that every electron will just spontaneously collapse. So it's all spread out, but its wave function just randomly localizes to some particular region of space. Very, very rarely, like if you have one electron and you wait for it to happen, it will happen like once every 100 million years, okay? But if I have lots of electrons, like in a table, there's way more than 100 million electrons in this table. There's billions and billions and billions of electrons. So somewhere in the table, all the time, an electron is localizing at one particular position, and because that electron is entangled with all the other electrons, the table maintains a location in space. And this is called spontaneous collapse, or GRW theory, after the initials of the people who invented the theory. And the great thing about GRW theory is that it's experimentally distinguishable from many worlds, because it says that if I have a collection of atoms, even if I'm not observing it, even if I'm not entangling it, one of the wave functions should spontaneously localize occasionally, and that will heat it up. Energy is not conserved in this theory. So people are doing experiments to test this. So it's really, legit experimental science.
Atoms, the current perception by the general public of atoms is that it's mostly empty space.
Yeah, that's a bad idea.
This is not true. Not correct, or not.
It's certainly not what many worlds says.
Right.
So this is, there are two enormous problems with our current way of presenting quantum mechanics. One is the measurement problem, which is this question like, what do you mean look at it? What do you mean observe? Like what actually happens? When does that happen? That's the measurement problem. But the other problem is what I unhelpfully call the ontology problem. Because ontology is the philosophy of being, of what is real, what is actually existing. So we just talked about hidden variable theories. So in Everett, what's real is the wave function. The wave function of the universe describes the universe exactly and completely. In hidden variable theories, there's a wave function and there's also particles. So there's extra ontology, extra pieces of reality. So the question of, is the atom mostly empty space, depends on what you think is real. So the wave function of the electron fills the atom. So if you're a many worlds person like me, you think what is real is the wave function. It fills up the atom, and the atom is not mostly empty space. The atom is the wave function. It has that size, right? You get the feeling that atoms are mostly empty space because you think that really the electron is a point, and the wave function is just telling you where you might see it.
When you measure it.
Well, yes. So many worlds says there's no such thing as where it is. There's only a probability of seeing it. Everyone knows that, but people kind of deny it. They talk as if there really is a location of the electron, even if they should know better. So people who say that atoms are mostly empty space are just being sloppy. They're just really thinking of the electron as a little tiny dot rather than a wave function. There is an exception to that, because there is a fourth version of quantum mechanics that is somewhat popular. I said three. I said many worlds, hidden variables, and spontaneous collapse. There's another version that just says, look, the wave function has nothing to do with reality. In many worlds, it's all of reality. In spontaneous collapse, it's all of reality, but it obeys different equations. In hidden variables, the wave function is part of reality, but there's also particles. In the other approach, which is called an epistemic approach to quantum mechanics, the wave function is just a way of talking about your personal knowledge of the world, your knowledge or lack of knowledge, your ignorance of the world. So your wave function is just a tool you use to make a prediction for what the experimental outcome is going to be, right? And that's more or less what we teach our students. And this approach says, don't bother about reality. What we should concern ourselves with is the experiences of agents who make predictions and update their probability expectations of the world. And so someone like that, if you ask them, how is an electron located in an atom, or how is it an atom mostly empty space? I think if they're honest, they would say, don't ask those questions. We don't ask reality questions. We just ask, what are you going to see kinds of questions. But I think that some of the less honest ones will say, sure, an atom is mostly empty space because an electron has a location somewhere. We just don't know what it is.
Why do they approach it in this, the way you're describing it, a sloppy way? Why do you think that is so common?
Well, it is part of the attitude that physicists have adopted, that we use quantum mechanics, but we don't try very hard to understand it. So you can talk to plenty of physicists on the street, and they will tell you to your face that understanding reality is not their job. And I think that's terrible, but
Right.
they will say it. And so when you press them too much on questions like, is the atom mostly empty space? What happens when we make an observation? They just kind of get uncomfortable and say, no, you're asking the wrong questions. Let's ask questions about what will we see at the Large Hadron Collider if we smash protons together, right? And those are perfectly good questions too, but I think that the what's really going on questions are also interesting. So because they don't care about these questions, they will often be sloppy in answering them, right? It is hard. Like you said, it's hard when you read the book. It's hard when you write the book. It's hard when you think about these things as a professional physicist. It's not natural. It's not easy. It's not intuitive. So even if you're a super duper expert at solving the equations and making predictions, understanding what's going on is a whole nother activity that a lot of physicists don't try very hard to do.
Now, how was all this stuff verified or argued? Like, say if you're sitting down, you're having a conversation with someone who espouses a competing theory. How are you guys working this out?
Good. I think that if everything were going along really, really well, we would be making experimental predictions and testing them. But I think the theorists have sort of dropped the ball here in the sense that the theoretical physicists should have, since the 1930s, been developing these alternatives, like many worlds, hidden variables, whatever, and using them to make predictions. But we really haven't. They were neglected. They were backwaters. There were a few people, a few plucky souls who really put their efforts into understanding these. Many of them got pushed out into philosophy departments. But that's what we need to do. We need to catch up on the last 70 years of lost time and work out what the implications are of these ideas. So the ball, I think, is in the theorist's court. The experimenters are working hard. Experimenters are doing amazing things with lasers and atoms and learning about how to manipulate quantum systems at a delicate level. But the theorists have not given them sharp experimental questions that would really illuminate the foundations of quantum mechanics. So honestly, what it is a bunch of people get around a table and talk to each other. They're like, all right, I think that what happens when the wave function branches is this. So a typical question we'll try to address is, in ordinary quantum mechanics, we say, if I send the electron through one way or I send it through the other way, there's a 50-50 chance that I will see it go left or go right. And someone says, what do you mean 50-50 chance? Especially in many worlds where there's a 100% chance there'll be a world where it goes left and a world where it goes right. What is the meaning of the phrase, there's a 50-50 chance? What is the nature of probability in this game where everything is perfectly deterministic, right? Mm-hmm. So that's not the kind of question that you answer very easily by doing an experiment. You have to think about it.
Right.
So that's the kind of thing that we argue about.
Now, how often do you guys get together?
It happens. There's conferences. It's a small community. Someone asked me just the other day, because the book came out, Something Deeply Hidden, last week, and I've been on book tour. So I was being interviewed, and someone said, how many people do you think in the world would classify themselves as working on the foundations of quantum mechanics? Maybe 100, something like that. Not a very large number. Like if you say how many people would classify themselves as particle physicists, it would be tens of thousands of people.
I remember there's a woman who came to the Comedy Store after the last podcast that we did, and she apparently is also working on it. And she was trying to explain it to me, her version of it, after hearing your version of it. It was very similar, but I believe she was from Romania, so she was struggling a little bit with English, but she was so excited to discuss it. It's so fascinating when you see someone who's for the limited number of how many of you guys there are and gals there are out there, I mean, whatever the number is, when that spark gets ignited and other people start tuning into it. She was so excited that this was being discussed on a podcast, and she wanted to talk to me about it, to say, please have more people on, please talk about this more. We need support. We need,
It does baffle me a little bit how difficult it is swimming uphill to get more support for this kind of thing, because it is just an enormous privilege to be able to call your job thinking about the fundamental nature of reality, right?
Yeah.
Like, I gave, my first book tour talk was last Tuesday, and I had dinner the night before with, several philosophers of physics in the New York area, from Columbia and NYU and Everett. And we're all friends, and we could talk about, our cats and our cars, but every single word discussed at the table all night long was about the philosophy of physics.
Is it because you guys work in isolation, essentially, and then when you get together, you're so pumped up to be discussing these things with like-minded souls?
In part, yeah. I mean, there's no one else in the physics department at Caltech who cares about these issues. I mean, some of them care in the sense that they are happy that I'm doing it, but no one does it really
but it's just
themselves. You. Yeah. Well, there's a couple other people in the philosophy department who care about these.
And a lot of folks, you were saying, get pushed into philosophy. And why is that? I mean, is it just because it's so complex, that it's so esoteric? There's so many people that just... They don't. The support for it's not there, but the support for philosophy is more common in mainstream.
Yeah, there's different kinds of support. One kind of support in academia is, who do you hire, right? What areas do you want? Like a physics department will generally say, yeah, we should have some people doing particle physics, some people doing astrophysics, some people doing condensed matter and solid state physics, and then it becomes hard. Do we need people doing biophysics? Do we need people doing this? And by the time they get to the foundations of quantum mechanics, there's usually very little support. Philosophers, their job is being patient and clarifying difficult conceptual questions. And so they get that quantum mechanics is fertile territory for philosophy. Like, one of the big problems in philosophy compared to science is that many of the questions that they're asking cannot be tested experimentally, right? What is infinity? Well, okay, it's hard to do an experiment there, but it's an important question, right?
Sure.
And so you need patience, but also it's harder to make progress because it's easy to be trapped by your intuition, right? Like when it's just you thinking and trying to think hard and be rational and so forth, it's easy to fall into a trap of, well, this looks reasonable to me. And quantum mechanics doesn't look reasonable to anybody. So it's a wonderful corrective. It's a wonderful reality check when you think, well, reality has to be this way. And then someone can say, well, look at quantum mechanics. That's different than what you said.
So philosophy and quantum mechanics, they sort of they share some sort of a border.
Yeah. Oh, yeah, absolutely. I mean, the things. So I was always a big fan of philosophy ever since I was an undergraduate, and I discovered it for the first time. But when I was an undergraduate, and my favorite philosophy classes were like the philosophy of morality or political philosophy, right? I took philosophy of science classes, but they seemed to be kind of dry to me because they were all about how scientific theories are constructed and chosen. The structure of scientific revolutions is the famous book that everyone reads. People like Thomas Kuhn and Paul Feyerabend and so forth. And okay, that's interesting, but it's sort of meta science, right? It's like how science is done, not how the world works. And it wasn't until, circa 2000 that I discovered that there are philosophers of physics who are kind of really doing physics. They're not asking how physics works. They're asking how the world works. But they're asking in a way that is comfortably located in philosophy departments and right now not so much in physics departments.
There was a part of the book that shocked me because I had a ridiculous idea once, and this idea was not my idea. Apparently, Laplace had a very similar idea as a thought experiment. I had an idea once that if one day there was a computer that was so powerful that it could accurately describe every single object on Earth, that we would be able to figure out the past. Yeah. And Laplace was saying that not only that, but he proposed for the entire universe, like every single object, electron, everything in the atom in the entire universe, that you would not only be able to show the past, but also predict the future.
That's right. So this is called Laplace's demon, although he never called it that. Pierre-Simon Laplace was a brilliant guy. He deserves to be much more well-known. So I think I've mentioned his name in every book that I've ever written for totally different reasons. He helped invent probability as we currently understand it, for example. But yeah, so Isaac Newton came up with the rules of classical mechanics in the 1600s, but it wasn't until Laplace around the year 1800 that this implication of classical mechanics was realized. It's a clockwork universe. That the way classical mechanics works is if you tell me the state of a system right now at one moment, by which in classical mechanics you would mean the position and the velocity of every part, and you knew the laws of physics, and you had arbitrarily large computational capacity, Laplace said a vast intelligence, okay, then to that vast intelligence, the past and future would be as determined and known as the present was. Because that's the clockwork universe. It's deterministic. Everything is fixed once you know the present moment. Now, quantum mechanics comes along and throws a spanner into the works a little bit. If you're a many worlds person, Laplace's demon is still possible. So if you know the wave function of the universe exactly, and you have infinite calculational capacity, you could predict the past and the future with perfect accuracy. But what you're predicting is all of the branches of the wave function. So any individual person inside the wave function still experiences apparently random events, right? So you can't predict what will happen to you, even if you can predict what will happen to the entire universe.
Whoo,
Yeah.
Sean Carroll. My goodness. There's a lot of people pausing this podcast right now, just shaking their head like...
You know, I wrote a little article that just appeared in Quantum magazine, which, by the way, if anyone here is a science fan, Quantum magazine is the best online magazine for science these days. They have really, really good high-level articles about all sorts of things. And so I wrote an article called What is Probability? Because, you know, again, this is a philosopher's kind of question. Like, you know, physicists will just put it to use and get on with their lives. Philosophers will say, well, what do you really mean by probability? The traditional answer is, if you're flipping a coin and you say it's 50-50, what you mean by that is that if you flipped it an infinite number of times, half the time it would be heads, half the time it would be tails. That's what you mean. It's called the frequentist idea of probability. But then what do you say, like, well, what is the probability that Donald Trump wins re-election? That's not going to happen an infinite number of times. You're not going to do the experiment. Or even better, what was the probability that Lee Harvey Oswald actually was the lone shooter of JFK? That already happened. That's in the past, right? But we can easily say, well, I think it was an 80% chance that that's true, right? So this is called Bayesian probability, where rather than thinking of an infinite number of things going on, you're assigning a degree of confidence to your lack of perfect knowledge, right? Like, I don't know exactly. There's
a great way to describe
something, there's something going on. I don't know what it is. So I assign a probability. And that just like a frequency, that, you know, the credence, as we say, that you assign to these different ideas is a positive number, then all the credences add up to 1 because something happened. So in quantum mechanics, is probability more like frequentist probability, or is it more like Bayesian probability? And the answer is it depends on what your favorite version of quantum mechanics is. In one of these spontaneous collapse theories, it's very much like a frequency. Like, you know, things happen randomly and it's purely objective. In something like in something like hidden variables, it's Laplace's demon all over again. So Laplace's demon doesn't work in a spontaneous collapse theory because the laws of physics are not deterministic. You don't know when things are going to collapse all by themselves. In a hidden variable theory, the hidden variables and the wave function evolve deterministically, but you don't know what the hidden variables are. So you can assign some probability to having them be different things. So there's some ignorance involved. Many worlds is the coolest idea because it's kind of, and this is what is kind of hard to wrap your mind around. On the one hand, there is only the wave function. It describes the universe exactly. But imagine that I measure the spin of an electron, okay? So I actually do know what the wave function is going to evolve into. It's going to evolve into a 50-50 split of I observed it spinning up and I observed it spinning down. But I only ever find myself in one side or the other. So there is always a moment in between when the wave function splits and when I know about it. It splits much faster than I can know about it. The speed of a wave function branching is some incredibly tiny number, 10 to the minus 20 seconds or something like that. And the time scale of things happening in my brain is like 10 to the minus 3 seconds at best, okay? So there will always be a time when there are two copies of me. One on the branch where the spin was up, one on the branch where the spin was down, but they're both identical. They don't know which branch they're on yet. So they need to be good Bayesians and say, well, what probability should I assign that I'm on one branch or the other? And it turns out that the probabilities work exactly like the textbook quantum mechanics tells you the probability should work out.
And how is that?
The wave function squared is the probabilities.
So the wave function squared.
Yeah, this is a rule called the Born rule after Max Born, who was the physicist who invented it. So, I mean, read the book, of course, but like you said at the very start, the history of quantum mechanics is just so fascinating and hilarious. Erwin Schrodinger of Schrodinger's cat fame, invented the idea of the wave function and wrote down the equation that it obeys, okay? But what he hoped was that if you had the wave function of an electron all by itself, if you solved his equation, it would sort of show that the wave function becomes localized, peaked at one location. The electron kind of acts like a point particle, and that's why we see particles. That was his hope. What actually happens when you solve the equation is that the electron spreads out all throughout the universe. So his hope was dashed. And then he's like, all right, I have this equation. What is it? Like, what does the wave function do? And it was Max Born, a whole other guy, who said, what the wave function does is you square it, and that's the probability of seeing something somewhere. Like if the wave function looks like this, it's some spread out thing, there's very small probability over here and large probability over there because the probability is the wave function squared. And Schrodinger said, like, oh my God, that's awful. I'm sad I had anything to do with it. He regretted being involved with this whole idea of probabilities and collapses and all that stuff.
Do you see an increased interest in this subject among students? I mean, this seems like
I do.
Yeah?
I do, but, with things like that, it's always hard to, protect against my own biases, right? Like I see, the people who are interested come to me because I keep talking about it, right? And maybe I'm, ruining their lives by getting them interested in it. When I have real graduate students, I try not to let them work on topics like this too much, like a little bit, get their foot wet, but they got to work on respectable stuff that will get them a job also.
That's interesting. So you're protecting them.
Oh yeah, no, I really try. Mixed success, of course, but I try very hard to be a good advisor in the sense that challenge them intellectually and get them to do interesting things, but in a way that will lead to a productive career. And part of that is get a job, right? Yeah. Like I'm not a believer in being such an idealist that you stop doing physics by the time you're out of graduate school. Keep going.
Do you think it's possible to boil this down to a documentary that isn't filled with woo, like just a response to something like What the Bleep, some sort of entertaining yet clear version of what you're saying?
I think so. Yeah. No, if there's any producers out there who want to option my book,
jump in, kids.
I think it's especially these days when computer graphics are really good, right, and we can visualize things that we couldn't visualize
that would
before.
Help.
Yeah, that was. In fact, I think that you got a copy of my book that didn't have any figures in it, right? Didn't you get the ARC?
I believe so. Yeah,
and that makes it much harder. The real book has pictures in it.
Oh, okay.
So that does make things hard.
Is that out, or is it?
Yeah, I'm sorry. I should have brought a copy.
Is that out today?
Last week.
Oh, okay.
So it is out now. We'll send you a copy, and then that'll be better. But honestly, all of the pictures in the book were made by me using Adobe Illustrator, and this is not really my area of expertise, so it's not like high-level graphics. It's just fairly functional. Especially, there's so much history in there. I had the idea, before I actually wrote this book, I was seriously contemplating writing a novel about the Bohr-Einstein debates because they were nominally about the nature of quantum mechanics, but they were really about the nature of reality, right? And there's all sorts of, the history is interesting. There were Nazis. We're talking about the 1930s, right? Einstein fled Germany. The personalities are very different. Niels Bohr is this amazing figure. I had David Albert on my podcast, on Mindscape, and the same David Albert who appeared in What the Bleep, and we talked about quantum mechanics and the measurement problem. And, he put it really well. He said, like, if there's a figure from history who I would like to have dinner with, it would be Niels Bohr. And because, he was certainly an amazingly good physicist, very, very influential. But over and over again, super duper smart people would get together and talk to Niels Bohr and come away spouting nonsense about the foundations of quantum mechanics. So somehow he had this magic charisma that worked in a bad direction to like make people just become crazy about quantum mechanics in a bad way. And that's part of the reason why we haven't dug into the foundations of quantum theory for so long.
What was it about him?
He was just incredibly charismatic in a weird way because he was a terrible writer. You know, there's this story where Einstein wrote this paper about entanglement and spooky action at a distance, and Bohr responded to it. And everyone said, you know, because by this time, 1935, people were already bored with the foundations of quantum mechanics, and they didn't want to think about it. So if anyone said, well, what about Einstein's worries? They would just say, oh, Bohr wrote a paper. Don't worry about it. And Bohr's paper was reprinted in this, you know, book you could buy. And then you could read it, and the pages were printed in the wrong order, and no one noticed.
No!
Yes. And it's just hard to make sense of what he said. So
Did people pretend to understand what it was saying, even though it was in the wrong order?
Yeah.
That's how weird it is.
That's how bad a communicator he was. But in person, everyone loved him. Like John Wheeler, who was Hugh Everett's advisor, was a sort of an acolyte of Bohr. And there's sentences he said, like, I never knew what people meant when they talked about people like Jesus or Socrates or Buddha until I met Niels Bohr. So he had some magnetism. That's why David Albert wanted to like meet him. He's like, what did that guy have? Like, What was it like to talk to him that people loved him so much, even though he was kind of wrong about the foundations of quantum mechanics?
But it's at least someone who's charismatic, who has that sort of enigmatic personality. At least it could spark interest.
Yeah, that's right. So, you know, part of the reason why I wanted to write this book is it's very much like, you know, another thing I do is go around and talk about science and religion. And I'm an atheist myself, so I say that, you know, science leads us to not believe in God. And I talk about this to very different audiences, churches and things like that sometimes.
How's that go?
Well, it depends very much on the age of the person in the audience is the thing. Older people, like, they've made up their minds. They're not going to change. But young people, even very, very, very religious young people, are fascinated by what I have to say. It's not that they change their mind right away, but it's like, oh, I've never heard someone put it that way before, right? And maybe they do change their mind later, maybe not, but at least they've heard a perspective that they were not exposed to earlier. I think the same thing is true with quantum mechanics. Like, there's a buttload of books about quantum mechanics on the market. Like, there's no shortage of books about quantum mechanics, but they're mostly with this spirit of, isn't this bizarre? Isn't this weird? We'll never understand it. And I think that many, many people who grew up to be physicists, this is what they're doing when they're 12 years old. They're reading these books, right? And so I wanted to write a book which said, like, actually, we could maybe understand this if we just tried. It's not ineffably mysterious. Let's you know, be embarrassed that the field of physics has not put its effort into it and make an effort here. And so maybe that will. So that's what my, you know, most ambitious hope for a book like this is, that 20 years from now, there'll be a flood of young physicists who think this is really interesting.
Yeah, well, the number, what would you estimate it would be currently? Like, how many people do you think worldwide?
It's certainly of order 100.
That's it?
I think so, yeah. Like, you know, when we have conferences, there's often 12 people there or 20 people.
Holy shit.
I mean, maybe there's more because I haven't met them all, but it always depends on how you draw the boundaries also. Whereas, yeah, there's thousands or tens of thousands of people in most subfields of physics. So, I mean, why would you go into the subfield where there's no money or promotion chances? it's tough.
Yeah,
that's why you become philosophers.
Yes, but still, that's stunning when you hear that it's somewhere around 100.
Yeah, I mean, we have, here in California, we have CQUIN, the California Quantum Interpretation Network, which is a group of us, you know, the people we know in California who care about these issues and who meet to talk about them. And it's like 15 people, something like that. And we could, and again, it depends on where you draw the boundaries and so forth.
But if one of you guys kicks the bucket.
I know, that's why we got to get new blood in there, you know.
Yeah.
But like I said, I do think it's growing, it's expanding, and I'm optimistic. I tend to be optimistic. You know, there is this. I alluded to it before, but let's emphasize it. We turned on the Large Hadron Collider in 2009. We turned it on in 2008, and then it exploded. Then we fixed it and turned it on again in 2009, and it found the Higgs boson in 2012. And it didn't find anything else. And that's bad. that's bad for physics in a big way, because it's great that we had a theory that came true with the Higgs boson, but in some sense we learned from the Large Hadron Collider the smallest amount it was possible for us to learn. There's a Higgs boson and that's it.
What about quark-gluon plasma?
Yeah, that's great, but we knew it was there. I mean, we'll learn details about it, but the fundamental underlying laws that give rise to that we've known since the 70s. So there's a million things we learn about, like for the gravitational waves, for measuring the Higgs boson. We pin down numbers. We measure the cosmic microwave background, the leftover radiation from the Big Bang.
But you would like something more that you could bring to people, saying that this is very valuable and tangible stuff.
Well, not just that. I wanted to make progress, right? So we had good reason to think that there should be a bunch of other particles that you would discover at the Large Hadron Collider, and they weren't there. Meanwhile, we have very good reason to think that 25% of the matter in the universe is dark matter, 25% of the energy in the universe, and we had very good reason to hope that we could detect it by now in an underground laboratory, and we haven't. And it's there, but it's beyond our reach somehow. So it's just so hard to make progress under these circumstances. And meanwhile, we have big, cool ideas like string theory that are hard to connect to the real world. So this is the last third of the book to me is, again, like I have my favorite ideas, but there's a bigger picture about what kinds of ideas we should pursue and how we should pursue them. So the last third of the book is maybe we need to understand quantum mechanics to better understand quantum gravity and the theory of everything, like how should we expect to understand quantum gravity if we don't understand quantum mechanics? Come on.
Right. And what was the motivation behind starting your podcast? It's called Mindscapes?
Mindscape, yeah. Mindscape. I've been having lots of fun with the podcast. It's been great. And several episodes about quantum mechanics. Most recently, just last week, I did a whole 2-hour solo episode on how space-time can emerge from quantum mechanics. I'll tell you, the motivation was when I wrote my previous book, The Big Picture. It was a sprawling book, so it was not only physics, but also philosophy and neuroscience and biology and math and computer science. There's a whole bunch of things in there that I'm not an expert on. I'm a big believer that people should talk about things they're not an expert on, but they should talk about them in some sense of humility that I don't understand everything here, so I will talk to some experts, right? So I went around talking to experts. I interviewed people. And I had so much fun because I was writing a book. I could literally just email a Nobel Prize-winning biologist and say, could I drop by and talk to you for an hour? And they would say yes. And when the book was done, that went away. I don't have the license to just call people up randomly and say, can I talk to you for an hour?
But if you have a podcast.
If you have a podcast, then suddenly, people want to talk to you, right? So I've gotten, I talked to Wynton Marsalis, the trumpet player, right? The Grammy-winning trumpet player. I talked to Seth MacFarlane the other day. I've talked to Nobel Prize winners, MacArthur Prize winners, philosophers, biologists, documentary filmmakers. I just really have a blast. So this podcasting thing, I think it's going to take off. You should look into it. Yeah.
Well, for me, there's no way I would be able to get someone like you to sit down and explain things like this without a podcast.
Well, it's taking advantage, I think, right? I'm not telling you this. Let's say we're telling the audience this, but we can talk as long as we want, right?
Yes.
Like you take advantage of this better than anybody. And it's different. It doesn't replace things like books, okay? But like books are always where you can get into the weeds a little bit, like maybe a little bit more specific, a little bit more careful. But there's a long road, there's a lot of books out there. I'm not going to read all of them. That was the other motivation behind starting my own podcast, is that I had a stack of books I wanted to read, and to force myself to read them, I would invite the author onto the podcast. But I can't read all those books. Which books should I read? There's a whole, journey to saying, this is important enough. I should dedicate myself to, a week of my time to reading this book. And hearing people talk about it in an informal setting is, both illuminating, but also like, there's ideas in there I really need to get to. So I'm a big believer in diverse ecosystems. I like Twitter. I like little YouTube videos. I like podcasts. I like books. I like talks. There's all sorts of ways to get this information.
Yeah, I think it's opened up the interest in a far broader group of human beings too, because in having conversations like this with you or with the hundreds of people that I get to talk to on a regular basis, it sparks ideas in people that in their seemingly mundane existence maybe just would never get in there. and it allows these new areas of inquiry and the new areas for them personally to go look into. And I get messages and I meet people all the time that tell me how much it's changed the way they view things because they've now been exposed to interesting information that's sort of sparked their view of the world in a different way, ignited different parts of their imagination. And
absolutely. And including me, like literally yesterday, one of the areas that I had hoped to get onto Mindscape podcast is economics. I'm very interested in economics, but I realized I don't know crap about economics. Like I'm not interested in, the trade deal or what interest rate the Fed should set. And the problem with economics is it's too relevant to the real world. So people want to talk about, monetary policy and things like that. But I want to talk about the underlying theoretical ideas, right? And I realized it's hard to get those. So I downloaded some economics podcasts and I started listening to them. And this happens to me all the time. When I'm listening to a good podcast, I'm in the car and I have to stop it to think about what just happened because, they said something and it gave me an idea. And the great thing about being a physicist is there's some relationship between what I do for a living and almost everything else, right? Like whether it's economics or biology or philosophy. So I can always say like, that's an interesting idea. I wonder if I should, write a paper about that. So, and I wouldn't have done that very easily without the podcast format. Yeah.
No, it's a really interesting time. It's a really exciting time to spread information. It's a really exciting time to find things that you're interested in.
Yeah. And also, I've always noticed this about the internet in general, which is that it calls you on your crap a little bit, right? Like before the internet, you could have opinions about things and you could spout off to your friends and, over the dinner table or whatever, over drinks. And suddenly when I started having a blog and I would spout off and people would say like, you're full of shit. Like, what are you talking about? How do you say that? And I have to, sit back and think like, oh, maybe I am full of shit. Like, where did I get that idea, right?
Yeah.
And I think that despite all of the misinformation, et cetera, that's out there, if you are intellectually responsible and want to get things right, putting your ideas out there in public to be critiqued is a wonderful tool. It really does go like, oh yeah. So like it helps you figure out like what I do understand and know and what just were kind of vague ideas that somehow got into my brain for no good reason.
Yeah, if you're open to the floodgates, that's the problem is there's so much feedback. Yeah. It's really hard to separate the wheat from the chaff.
It is, yeah. And, different people have different strategies. Like when I talked to Seth MacFarlane, it was interesting. He reads the comments. Like he wants to know.
Doesn't he have like 12 million Twitter followers or something crazy?
And he hates it. He's like, it's poisonous and toxic. But he reads them. Yeah. And for good reasons. He's like, look, I'm creating entertainment. Like if I don't know what the people I'm trying to reach think about it, what is the point? It's like much like me in physics. Like the kind of physics I do is not building a better machine or curing cancer, right? It's only because human curiosity leads us there. So if I don't tell other people about it, what's the point? And but we did have a conversation about blocking people on Twitter because I was like, the only reason why I like Twitter is because I block everyone who's a jerk. Like if they make my Twitter experience less pleasant, they get blocked right away.
Yeah, that's a good move.
Yeah,
there's a lot of loud noise.
And there's a lot of wonderful people.
Yes.
I've met wonderful people. Like half of my podcast guests come because I got to know their Twitter feeds and became fascinated.
Yeah, I read a lot of other people's things. I don't read any of my stuff, like any of the stuff that's coming at me. It got too overwhelming after a while. And it also it interferes with the time that you have to put stuff out. Because people get wrapped up in responding to their mentions or reading their mentions, and there's an extraordinary amount of time that you can waste doing that.
Yeah, I mean, that's the secret. Like, people ask, like, how can I spend so much time on Twitter? And I'm like, what are you talking about? Like, I spend 5 minutes a day on Twitter tweeting and maybe another 15 minutes reading other people's tweets and 0 time responding to tweets. That's the secret.
Yes.
Like, if you Twitter's a terrible medium for conversing.
Right.
You just can't be precise. You can easily misunderstand, and people easily become aggressive jerks, right? So it's the worst possible way to have a back and forth unless you already know somebody and are just trying to clarify something. So I use it for linking to things. Like I say, Twitter is for linking, not for thinking. It's not.
Yeah, it's like the hierarchy of communication. Top of the food chain is one-on-one talking. Just two people having a conversation, and especially without any sort of heightened sense of importance or anger or frustration with that other person. Just two people talking. That's number one, like with no gravity, right? Number two is probably phone calls, like calling someone. Then you don't see them. It's not as good, but like being in front of someone physically one-to-one is the best way to do it, which is one of the reasons why I love podcasts as well, is because you get a chance to put that energy out there, the energy of a one-on-one actual conversation with people, as opposed to writing an article. Like, I'm sure you've had snarky articles written about you. It's weird. It's like, well, I wouldn't say that. Like, why are you saying it that? Well, you're determining my thoughts, and
I've almost gotten to the point where I never respond to those, but I get a lot of them. I mean, I get a lot of them.
I'm sure.
When you started the podcast, was it always in a studio, or did you do things remotely back in the day?
We've only had a few conversations remotely through Skype, and one of them was with this Egyptologist, John Anthony West, who was in poor health. He's since passed away, and then we eventually did get him into the podcast studio. But I started doing it in my house, and just with friends. I mean, there was no grand ideas when this thing got started. It was just comics fucking around, and then slowly but surely, I'll be like, I wonder if that guy would talk to me, and then it became what it is.
I am still a hefty portion of my interviews are still remotely, because like I want to get this person, they're in Oklahoma and whatever. But I totally think that it's much better if you're in person. So whenever I can do that, like I lug my little portable podcast studio around. So if I going to Boston in a few weeks, I'm going to try to get like 10 people on the podcast. So
no, that's great, man. I'm excited you're doing it, and thank you for writing the book, and thank you for coming in here and talking about it. And if people want to get your podcast, it's available on iTunes. It's
wherever
everywhere.
Podcasts are sold. Yeah.
Anything else?
Many things, but this is good. Yeah. The podcast and the book are the things I'm hearing.
All right. Well, always a pleasure, Sean. Thank you very much.
A lot,
Thanks
Joe.
for being here. Bye, everybody.